Mercury is the smallest planet in our solar system and the one closest to the Sun, which gives it unique characteristics unlike any other planet. Despite its proximity to the Sun, Mercury has an array of paradoxical features that continue to intrigue scientists and astronomers alike. It is a world of extremes, with one side baking in intense heat and the other plunging into the freezing cold of space. To fully understand Mercury's role and significance within the solar system, it is important to delve into its composition, surface features, atmosphere, and its relationship with the Sun. Mercury's orbit is highly elliptical, meaning its distance from the Sun varies considerably throughout its journey. At its closest approach, Mercury is just 46 million kilometers, about 29 million miles, from the Sun. In contrast, when it reaches its farthest point, the distance extends to roughly 70 million kilometers, 43 million miles. This elliptical orbit contributes to significant changes in temperature across the planet, creating stark differences between its day and night sides. The planet's extreme temperature variations make it one of the most fascinating celestial bodies in our solar system. During the daytime, Mercury's surface can reach temperatures as high as 430 degrees Celsius, 800 degrees Fahrenheit. This intense heat is enough to melt metals like lead or zinc. However, when night falls, the temperature drops drastically to minus 180 degrees Celsius, minus 290 degrees Fahrenheit, a plunge so severe that even nitrogen freezes solid. This dramatic contrast is largely due to Mercury's lack of a substantial atmosphere. Without an atmosphere to trap heat, like Earth's greenhouse effect, Mercury rapidly loses heat when it rotates into the dark side. This thin, almost negligible atmosphere, called an exosphere, is composed primarily of oxygen, sodium, hydrogen, helium, and potassium. The lack of a dense atmosphere also explains why Mercury is constantly bombarded by solar radiation and micrometeorites, resulting in a cratered and weathered surface. Many of these craters are remnants of impacts that occurred billions of years ago, during the early stages of the solar system's formation. The largest and most significant of these craters is the Caloris Basin, an immense impact structure over 1,550 kilometers, 960 miles, in diameter. The force of the impact that created this basin is believed to have been so intense that it caused the planet's surface to ripple, forming concentric rings of mountains and valleys. Mercury's surface is a reflection of its tumultuous past. In addition to craters, there are vast plains of solidified lava flows, believed to have formed from ancient volcanic activity. These lava plains cover significant portions of Mercury's surface, contributing to the planet's relatively smooth regions. Over time, as Mercury's interior cooled, the planet began to shrink, creating long, steep cliffs known as lobate scarps. These scarps, some of which stretch for hundreds of kilometers and rise several kilometers high, indicate that Mercury has experienced tectonic activity, a rare phenomenon among the solar system's smaller planets. Interestingly, despite its small size and close proximity to the Sun, Mercury possesses a magnetic field, a feature more commonly associated with larger planets like Earth. Mercury's magnetic field, although weaker than Earth's, is generated by the movement of molten iron within its core. This suggests that beneath its rocky exterior, Mercury has a large, partially molten core composed primarily of iron. In fact, Mercury's core makes up about 85% of its radius, an unusually high ratio compared to other planets. This large core is not only responsible for the magnetic field, but also plays a crucial role in shaping Mercury's geological features. Due to its weak magnetic field, Mercury is constantly bombarded by charged particles from the solar wind, which occasionally interact with the planet's surface, causing chemical reactions that release particles into the exosphere. These interactions, combined with the planet's lack of atmospheric protection, leave Mercury vulnerable to the Sun's relentless radiation. However, this also makes Mercury a valuable object of study for scientists who are interested in understanding how planets without atmospheres or strong magnetic fields can survive in such extreme conditions. Mercury's slow rotation adds another layer of complexity to its already unusual characteristics. A single day on Mercury, the time it takes for the planet to rotate once on its axis, lasts approximately 59 Earth days, meaning that the planet rotates very slowly compared to Earth. This slow rotation, coupled with its elliptical orbit, results in a phenomenon known as solar day length, which causes one solar day on Mercury, the time between one sunrise and the next, to last about 176 Earth days. This peculiar cycle of long days and rapid temperature changes creates an environment unlike any other planet in our solar system. Despite these extreme conditions, Mercury is not a lifeless wasteland. Scientists have found evidence of water ice in permanently shadowed craters near the planet's poles. These regions, which never receive direct sunlight, are cold enough to preserve ice that may have been delivered by comets or formed from interactions between Mercury's surface and solar particles. The discovery of water ice on Mercury was a surprising and exciting revelation, as it suggests that even the hottest planet in the solar system has pockets of frozen material that have persisted for millions, if not billions of years. Mercury's long history and diverse landscape make it a key target for scientific exploration. Over the years, space missions such as NASA's Mariner 10 and Messenger have provided valuable data on Mercury's surface, magnetic field, and composition. Mariner 10, which flew by Mercury in the mid-1970s, was the first spacecraft to capture detailed images of the planet's surface, revealing its cratered and rugged terrain. Decades later, Messenger orbited Mercury between 2011 and 2015, conducting detailed surveys of its magnetic field, exosphere, and geological features. Among Messenger's many discoveries was the confirmation of water ice at the poles and the identification of unusual hollows on the planet's surface, shallow, irregular depressions that appear to be unique to Mercury. These hollows are thought to be formed by the sublimation of volatile elements, such as sulfur, which are exposed to the harsh solar environment. The process by which these hollows form remains a topic of ongoing research, as scientists continue to unravel the mysteries of Mercury's dynamic surface. In terms of its size, Mercury is only slightly larger than Earth's moon, with a diameter of about 4,880 kilometers, or 3,032 miles. Despite being the smallest planet in the solar system, its dense iron core gives it a relatively high gravity compared to its size. Mercury's gravitational pull is about 38% that of Earth's, which means that a person weighing 100 pounds on Earth would weigh only 38 pounds on Mercury. This combination of small size and high density is another distinctive feature that sets Mercury apart from the other planets. Mercury's lack of atmosphere and proximity to the Sun also result in the planet having an unusual twilight effect. Because there is no substantial atmosphere to scatter sunlight, the sky on Mercury remains pitch black, even during the daytime. When the sun rises or sets on Mercury, there is no gradual transition from day to night or from night to day as we experience on Earth. Instead, the sun simply appears or disappears from the horizon, leaving behind a stark contrast between light and dark. This absence of a twilight period is just one of the many ways in which Mercury defies our expectations of what a planet's environment should be like. One of the most significant factors that makes Mercury a unique planet is its relationship with the Sun. Mercury's elliptical orbit and slow rotation result in complex interactions with the Sun's gravitational forces, creating what is known as a resonance between its orbital period and its rotational period. For every 2 orbits Mercury completes around the Sun, it rotates exactly 3 times on its axis. This 3-to-2 spin-orbit resonance is rare in the solar system and results in a peculiar phenomenon. The Sun appears to briefly stop in the sky, reverse direction, and then move forward again as seen from certain points on Mercury's surface. This unusual motion of the Sun, combined with the planet's long days and short years, a year on Mercury lasts only 88 Earth days, gives rise to strange day-night cycles and periods of extreme solar exposure. At some locations on Mercury's surface, an observer would see 2 sunrises during a single day. First, the sun would rise, pause in the sky, set again briefly, and then rise once more before continuing its journey across the sky. These odd celestial movements contribute to the extreme temperatures and help to highlight the intricacies of Mercury's position and motion in the solar system. Mercury's orbit also plays a role in its visibility from Earth. Because the planet is so close to the Sun, it can be difficult to observe without specialized equipment. Mercury is often only visible for short periods, either just before sunrise or shortly after sunset, appearing as a small, bright point of light near the horizon. This proximity to the Sun makes it one of the least observed planets, even though it has been known since ancient times. Early astronomers such as the Babylonians, Greeks, and Romans recognized Mercury, and it was associated with speed and swiftness due to its rapid movement across the sky compared to other celestial objects. Despite Mercury's elusive nature, modern space missions have provided invaluable insights into its composition and characteristics. One of the most ambitious missions to study Mercury is the joint European-Japanese BepiColombo mission, which was launched in 2018. Named after the Italian mathematician and engineer Giuseppe BepiColombo, who helped explain Mercury's spin-orbit resonance, the mission is designed to study the planet's magnetic field, surface features, and composition in unprecedented detail. BepiColombo consists of two spacecraft, the Mercury Planetary Orbiter, MPO, which focuses on mapping the planet's surface and analyzing its geology, and the Mercury Magnetospheric Orbiter, MS, which studies the planet's magnetosphere and the interaction between Mercury and the solar wind. These two orbiters will work together to provide a comprehensive view of Mercury's environment, from its core to its exosphere. The mission is expected to answer many of the remaining questions about the planet's magnetic field, volcanic history, and potential for harboring water ice at the poles. One of the key questions scientists hope to address with BepiColombo is the origin of Mercury's large core. Mercury's core, which accounts for a significant portion of its mass, is much larger than expected for a planet of its size. This has led to several hypotheses about how the planet formed. One theory suggests that Mercury was once much larger, but lost most of its outer layers due to a massive collision early in the solar system's history. This event would have stripped away the planet's lighter materials, leaving behind the dense iron core we see today. Another theory proposes that Mercury's proximity to the Sun caused its lighter elements to evaporate during its formation, leaving a mostly metallic body behind. Both theories are plausible, but neither has been definitively proven. The data from BepiColombo could provide crucial evidence to support one hypothesis over the other, helping scientists better understand the processes that shape not only Mercury, but also the early solar system as a whole. In addition to investigating Mercury's origins, BepiColombo is tasked with studying the planet's magnetic field in detail. One of the most surprising discoveries made by the MESSENGER mission was that Mercury's magnetic field is offset from the planet's center by about 20%. This asymmetry is unlike anything seen on Earth or other planets with magnetic fields, such as Jupiter or Saturn, and scientists are eager to learn more about its cause. Theories suggest that this offset may be related to Mercury's unique internal structure, particularly the size and composition of its core, or to the way its core cools and generates magnetic activity. Understanding Mercury's magnetic field is important not only for planetary science, but also for studying space weather and the effects of solar wind on planets without thick atmospheres. Mercury, with its weak magnetic field and thin exosphere, provides a natural laboratory for observing how a planet interacts with the Sun's powerful solar wind. The data from BepiColombo could shed light on these processes and provide valuable information for understanding other planets, such as Mars, that also have weak or absent magnetic fields. As we learn more about Mercury's internal structure and magnetic properties, it becomes clear that this small planet holds important clues about planetary formation and evolution. Its geological features, including vast lava plains, towering cliffs, and deep craters, offer a window into the violent history of the early solar system. Many of the processes that shape Mercury, such as volcanic activity, impacts from asteroids and comets, and tectonic forces, are similar to those that have shaped Earth and other rocky planets. However, because Mercury has no atmosphere or active geological processes today, its surface has remained largely unchanged for billions of years, preserving a record of these ancient events. For example, Mercury's volcanic history is a topic of great interest to planetary scientists. MESSENGER data revealed that much of the planet's surface is covered by ancient lava flows, indicating that Mercury experienced significant volcanic activity early in its history. These lava flows likely played a key role in shaping the planet's surface, filling in craters and forming vast plains. However, Mercury's volcanic activity appears to have ceased long ago, with no evidence of recent eruptions or active volcanism today. One of the key features associated with Mercury's volcanic past is the presence of pyroclastic deposits on the planet's surface. These deposits are formed by explosive volcanic eruptions that release gas and molten rock into the air, creating distinctive patterns on the ground. Pyroclastic deposits have been found in several regions on Mercury, suggesting that some of the planet's volcanic activity was driven by gas-rich magma. This discovery was surprising, as scientists previously believed that Mercury's small size and close proximity to the Sun would have caused any volatile elements, such as water or carbon dioxide, to evaporate during its formation. The presence of these deposits indicates that Mercury may have retained more volatiles than initially thought, providing new insights into its geological history. The importance of studying Mercury extends beyond just understanding the planet itself. As we explore planets around other stars, known as exoplanets, the lessons we learn from Mercury can help us interpret data from distant worlds. For example, Mercury's extreme temperatures, lack of atmosphere, and peculiar orbit provide a useful analog for understanding rocky exoplanets that orbit close to their host stars. Many exoplanets discovered by missions like NASA's Kepler Space Telescope are hot Jupiters or super-Earths, planets much closer to their stars than Mercury is to the Sun. By studying Mercury's interactions with the Sun, such as its surface temperature variations and the effects of solar wind, scientists can develop models to predict the conditions on these exoplanets. Additionally, Mercury's magnetic field, although weak compared to Earth's, raises questions about the magnetic fields of other planets, both within and outside our solar system. Magnetic fields are critical for protecting planets from the harmful effects of solar radiation, and the presence or absence of a magnetic field can have a significant impact on a planet's habitability. The data collected by missions like Messenger and BepiColombo could help scientists determine whether magnetic fields are common on rocky planets and how these fields influence planetary atmospheres and climates. Mercury's polar regions also offer an unexpected source of interest, particularly with regard to the possibility of water ice. Despite being the closest planet to the Sun, Mercury's poles contain permanently shadowed craters where temperatures remain cold enough to preserve water ice. This ice, thought to have been delivered by comets or formed through interactions with solar wind particles, is a surprising find on such a hot and airless world. The discovery of water ice on Mercury has significant implications for our understanding of the distribution of water in the solar system and raises intriguing possibilities for future exploration. Water is a key ingredient for life as we know it, and the presence of ice on Mercury, even in such small quantities, suggests that water may be more common in the solar system than previously thought. Although Mercury itself is not a candidate for life, the fact that water can exist in such a harsh environment challenges our assumptions about where life-sustaining elements can be found. This discovery has encouraged scientists to look more closely at other small, airless bodies in the solar system, such as asteroids and moons, to see if they too might harbor water ice in their shadowed regions. In the context of human exploration, understanding the distribution of water in the solar system is critical. Water could be a valuable resource for future missions, providing not only hydration for astronauts, but also a potential source of oxygen for breathing and hydrogen for rocket fuel. Mercury's ice deposits, though challenging to access, could one day become important for long-term exploration of the inner solar system, serving as a model for how we might utilize resources on other planets and moons. Looking ahead, BepiColombo's ongoing mission promises to deliver even more discoveries about Mercury. As the spacecraft continues its journey and eventually enters orbit around the planet, scientists eagerly await new data that will expand our understanding of Mercury's surface, magnetic field, and internal structure. These insights will not only help us understand how Mercury evolved, but will also provide a broader perspective on the formation and evolution of rocky planets in general. One of the key objectives of the BepiColombo mission is to map Mercury's surface in greater detail than ever before. By using advanced imaging techniques and spectrometers, the spacecraft will create high-resolution maps of the planet's geological features, revealing subtle details about its composition and history. These maps will help scientists identify regions of interest for future study and may even uncover previously unknown surface features. In addition to mapping, BepiColombo will investigate Mercury's exosphere, the thin layer of gases that surrounds the planet. Mercury's exosphere is composed of elements like sodium, potassium, and calcium, which are constantly being ejected from the planet's surface by solar wind and micrometeorite impacts. Understanding the composition and dynamics of Mercury's exosphere is important for understanding how the planet interacts with its environment and how similar processes might occur on other airless bodies in the solar system. BepiColombo's study of Mercury's magnetic field will also provide new insights into the planet's internal structure. By measuring the strength and direction of the magnetic field at various points around the planet, scientists can infer details about the size, composition, and behavior of Mercury's core. These measurements may help resolve long-standing questions about why Mercury's magnetic field is weaker and more asymmetric than Earth's, and could provide clues about the processes that generate magnetic fields on other planets. Mercury's significance in the realm of planetary science goes beyond its proximity to the Sun and its extreme conditions. As a planet that straddles the line between a common rocky planet and a unique outlier, Mercury offers a wealth of knowledge for researchers, exploring not just the evolution of planets, but also the conditions that allow planets to maintain atmospheres, magnetic fields, and even water ice. As we push the boundaries of space exploration, understanding how and why Mercury deviated from its planetary siblings in certain key aspects can lead to groundbreaking insights. One such insight revolves around the planet's interior. Mercury is an enigma because it has an unusually large iron core relative to its size. This iron core makes up about 85% of Mercury's radius, a far greater proportion than that of Earth, Mars, or Venus. This discovery, confirmed by data from the Messenger spacecraft, raises critical questions about how planets form and what factors lead to such drastic variations in their internal structure. The most widely accepted theory suggests that Mercury may have once been much larger, with a mantle and crust more similar to Earth's, but that a series of massive impacts during the early solar system stripped away much of its outer layers. This hypothesis is supported by the planet's high density and its lack of volatile compounds, which would have been lost in the heat generated by such collisions. If this theory holds true, studying Mercury could give scientists valuable clues about the destructive impact events that were common in the early solar system and how they shaped the evolution of the planets we see today. Another possibility is that Mercury's formation was influenced by the intense heat and radiation from the young sun. As the planet formed close to the sun, it might have been subjected to extreme temperatures, which would have caused lighter elements to evaporate and escape, leaving behind a planet with a high concentration of heavier materials like iron. If this is the case, then Mercury provides a glimpse into how proximity to a star affects planetary composition, a factor that will be crucial for understanding the many exoplanets that are being discovered in tight orbits around their stars. Mercury's core is also intriguing because, despite its size and composition, it is still partially molten. This fact is puzzling to scientists, as the planet is relatively small and should have cooled completely billions of years ago. The presence of a molten core suggests that Mercury may have an inner heat source, or that its cooling process has been slowed by unknown factors. Understanding why Mercury's core has remained partially liquid could help researchers refine their models of planetary cooling and core dynamics, which are essential for studying the magnetic fields and geologic activity of planets. The planet's magnetic field is another mystery that continues to fascinate scientists. Mercury is the only other rocky planet in the solar system besides Earth that has a global magnetic field, though it is much weaker than ours and exhibits a pronounced asymmetry, with the magnetic field being stronger in the northern hemisphere than in the southern. This asymmetry has baffled scientists, and one of BepiColombo's main objectives is to provide more detailed measurements of the magnetic field to help determine what might be causing this imbalance. Understanding Mercury's magnetic field is not just a matter of academic curiosity. Magnetic fields are critical for protecting planets from harmful solar and cosmic radiation. Earth's magnetic field, for instance, plays a crucial role in shielding our atmosphere and surface from solar winds, which would otherwise strip away our atmosphere and make life as we know it impossible. The fact that Mercury has a magnetic field, despite its small size and lack of a thick atmosphere, challenges existing models of how planetary magnetic fields are generated. By studying Mercury's field, Scientists hope to gain insights into the processes that govern magnetic fields on all planets, including potentially habitable exoplanets. Moreover, Mercury's magnetic field interacts with the solar wind in unique ways. The planet's lack of a substantial atmosphere means that its surface is directly exposed to particles from the sun. These interactions create a dynamic environment around the planet, with solar wind particles being funneled by the magnetic field toward the surface. This process can release atoms from Mercury's surface, contributing to the planet's thin exosphere. By observing how these interactions play out on Mercury, scientists can improve their understanding of space weather and its effects on planets with weak or absent atmospheres, including Mars and certain moons in the solar system. Mercury's extreme conditions and proximity to the sun make it an ideal laboratory for studying the effects of solar radiation on planets. As the sun ages, it will go through phases of increasing intensity before eventually becoming a red giant and then a white dwarf. Studying Mercury gives scientists a glimpse into the long-term effects of solar radiation on planetary environments. In particular, understanding how Mercury's surface, exosphere, and magnetic field respond to solar wind and radiation can help scientists predict how other planets, including Earth, might evolve as the sun changes over the next billions of years. In the broader context of solar system exploration, Mercury offers a valuable reference point for understanding the diversity of planetary environments. By comparing Mercury to other rocky planets, especially Earth, Venus, and Mars, scientists can better grasp the full spectrum of planetary formation and evolution. Mercury's small size, proximity to the sun, and unusual interior structure make it a unique case study, but the principles learned from studying it can be applied to many other worlds, both in our solar system and beyond. In addition, Mercury's water ice deposits in its permanently shadowed craters challenge our assumptions about where water can exist in the solar system. Water is a key factor in the search for life, and finding it in unexpected places like Mercury suggests that it may be more widespread than previously thought. The implications of this discovery extend beyond Mercury itself, as it encourages scientists to look more carefully at other, seemingly inhospitable places for signs of water and other life-sustaining materials. Mercury's study is also essential for the future of human exploration. While Mercury itself may not be a prime target for human settlement due to its extreme temperatures and lack of atmosphere, the knowledge gained from exploring the planet will be invaluable for future missions to other planets and moons. For example, the challenges of operating in Mercury's harsh environment, including managing extreme heat and cold and surviving in a low-gravity, airless world, will help engineers and scientists develop the technologies needed for more ambitious missions, such as sending humans to Mars or establishing a permanent base on the Moon. Conclusion: Mercury's legacy in planetary science. As we continue to explore the solar system, Mercury remains a crucial piece of the puzzle in our quest to understand the origins and evolution of planets. From its peculiar orbit and rotational dynamics to its surprisingly complex interior and magnetic field, Mercury defies easy classification and continues to surprise scientists with new discoveries. The lessons learned from studying Mercury have profound implications, not just for understanding the planet itself, but for developing a broader picture of planetary science and the processes that shape worlds both near and far. The ongoing BepiColombo mission holds great promise for expanding our knowledge of this enigmatic planet, and future missions may unlock even more secrets. As we push the boundaries of space exploration and continue to uncover the mysteries of Mercury, we are reminded that even the smallest and most distant planets have much to teach us about the universe and our place within it.